types of identifiers that are used in C. Then we go on to compilers and interpreters, so that we can understand that when we say this is a compiled program and this is an interpreted program and so on and so on, what are we talking about? Right. So this is how you look at the computer organization in general. So we have different levels of computer organization in the architecture, right? So at the upper end, or the higher level, we have a desired behavior that we want to do. Let's say you just want to print or calculate something. That is what you have access to as a user, right? But below that, for that to happen, there should be an algorithm that is running in order to perform that task. In that algorithm will be running due to a programming language. So you write your algorithm in a certain programming language, then the algorithm will run. Then the programming language will also go down to the instruction set architecture, whereby whatever you've written is now taken back and then represented as something that is close to the machine. Then you have what is called the microarchitecture, right? In other words, we are now dealing with how those instructions will activate the hardware. Then we have what are called the logic gates, whereby now we have a function being defined as an AND, OR, and so on and so on. And these will be activated through the transistors. And the transistors have electrical signals that are actually passing between the memory locations and so on and so on. So in other words, whatever you are writing here, let's say you are saying do this and that, remember that this do will be reduced until it becomes an electric signal that can activate maybe a screen, maybe a sound device, and so on and so on. So if you remember what we're talking about in terms of computer architecture, we said that we need signals to move between these transistors so that we can have our memory locations as a series of ones and zeros and the like. But at your user level, you are just writing do if whatever, whatever, else, whatever, whatever. But then this doesn't make sense to the computer or to the machine until it is now presented in a way that the computer can understand, which is a series of signals that becomes ones and zeros. So we have the user level, what we want to do. Then we have the software level. With this, you can write your software. Then we have the hardware levels, whereby your program now is now converted to a hardware instruction that will produce the electric signals. Okay, so this is what you should understand even when you are writing a program, that at the end of the day, it should go down to the series of ones and zeros as electrical signals, right? So what we have in terms of levels of software languages, we have what is called machine language, which is ones and zeros. This is the language which is understood by our hardware, right? Then there's an assembly language, right? So this converts the assembler, it converts the assembly language into machine language, right? So this may be the load accumulators and the like something that you can be understood when you are writing it. And then the assembler will convert these two to machine language ones and zeros, right? Then we have higher levels. In this case, we are just looking at C, whereby now we are writing our English like statements, do, while, and then so on and so on. And these will be then converted first to assembly language, then next to the machine language so that they can activate our hardware. So those are levels of our softwares or languages. So we now look at compilation. So when I talk about a compilation, we're saying you are converting a source code, that is the do whiles, to an object code. This is usually in hexadecimal and the like, right? Maybe it becomes one of the assembly languages. So you are not going to do the conversions on your own, but then when C sees this and you are compiling your program, then it converted to object code, right? Let's look at an example. Let's say you sum A plus B, right? Then this compiles to machine language, load register 1 with A, load register B with that, add R1, register 1 and register 2, store your results in R1 or in the right. Then, when we talk about source code, we are talking about the language in which the program was written. So it can be C, it can be C++, and the like. Then the object code is the machine language equivalent to that program after being compiled, right? Then a compiler is a software program that will translate the source code into the object code, right? So an assembler is a special case of a compiler. Why? Because the assembler will change assembly language to machine code, right? In other words, when the code was already written in assembly language, then it becomes a compiler which compiles it to machine code, right? So how do you do when you want to compile your program? First, you have to create or edit a source code. That means you should write a program, maybe in C or in C++. That's the first thing you have to do. You should write the program. Then after that, you now compile the source. It's just a button click because of our graphic user interface, right? Then you link the object modules together. This is again done by C. It creates the links according to your program. Then you test. So this will create the executable program, which you find as .exe, right? That's the executable program. So this is now the program which, if you double click, it will run and show you what is happening. But now with the new platforms for programming, you realize that you do all this by just clicking the mouse, okay? Then if there are errors, you start over again, you edit your source, compile again, and come back. So the process whereby you are now removing the errors and the like, that's where we talk about the debugging your program. So that's how you compile. But like I'm saying, with the platform that we are using dev.c for this course. So you can just download dev.c. Sometimes it comes with dev.c++, but we will need dev.c. You can also find code blocks and the like. You can use it for your programming, right? So we are saying all these steps now, you just click and you get your good results. So this is an example program. So you can write your program, include stdio.header, int main, you open your main function, printf good morning, return 0. So this will print good morning, right? This is an example of source code, right? So you just save it as C source code. then you can compile. Like I'm saying, some of these steps now, because you'll be writing on a programming platform, some of the steps will not be there, right? So what happens in compilation? You invoke the compiler on a source program to generate machine language equivalence. So you realize that on our dev-C platform, you just click compile, then it compiles. Some will give build, then run, depending on the platform. Then the compiler translates source code to object code and saves the object output as a disk file. Well, some of this don't apply now because just save it as C and it will just save it on your disk, like said. Then the large systems may have many source programs. That means the good morning program is just an example. It's a small program, but you can have bigger programs to use. Then each source code has to be compiled, right? Then how do you link the object modules? You combine them together to form an executable file. You take multiple object modules, then the linker takes object modules and it creates executable files for you. The linker will resolve references to other object modules and then those calls to external libraries and creates an executable file. Like I said, some of these things are no longer visible to you because of the programming platforms that we have. Then you go on to interpretation or interpreted language. There is no linking and there is no object code generated, right? So in this case, the source statements are executed line by line. So what we're talking about is in a compiled language, you build a block of an executable file. Then when you are running it, you execute it once, right? But in an interpreted language, it executes line by line without generating any object code, right? So what happens when interpreting? You read the source line, then it passes the line, then it does what the line says. Allocate space for variables, execute arithmetic operations, and the line, then go back to step number one, read the line, pass the line, and do what it says, and so on and so on. All right. So this is similar to the instruction cycle. Okay. As an example, this is a Perl script, right? It's an interpreted language. So it's print.pl, then print good morning, right? Then this line, it will be passed to the print predefined statement. Then it prints what should be there. Then when you're using shell, it print.sh. Then this, if you ever saw something like in Linux, they use the word echo to produce output. Then good morning, then this line is passed and then executed. So this executes line by line. That's an interpreted language. So the main difference between an interpreted language and a compiled language is because in the compiled language, you create an object code which creates an executable file, and then you can just execute it at once. In an interpreted language, it is done line by line. Right. So what are the advantages of compiling? It's faster execution, single file to execute. And the compiler can do better diagnosis of syntax and semantic errors since it has more information than an interpreter. The interpreter only sees one line at a time. So it means there's an issue of logic. That issue might not be easily diagnosed in an interpreter, right? Then the compiler can also optimize code. Disadvantages, it's harder to debug because it's one big page that you're dealing with. takes longer to change source code, recompile, and relink because of the need for the linkages and compilation, right? In an interpreter, it's easy to debug since you are going line by line. Faster development time because there is no need for the compilation, creation of object code, and so on and so on. Advantages: slower execution times because of the line to line, and there is no optimization, and it needs all the source code that is available at once, right? And the source code is larger than executable for larger systems, right? In some interpretive systems, like BASIC, Perl, and Lisp, these are interpretive systems. Then operating system interfaces, C shell, Bourne shell, Linux, those are also interpretive systems. That means they use interpreters, not compilers. So many different ways of developing systems. There's always a trade-off between system development, testing, debugging, and performance etc. So we're looking at, when you are looking at compiled languages in the interpreted languages, we are also looking at many different things like how long it takes to develop, how easy it is to debug, and what is the performance, how much support do you have for that when you are choosing a programming platform. Okay, so that is basically what we look at when we talk about interpreters and compilers. Okay.